Hello everyone, my name is Xiao from Kaust. I'm the author of ChemPlasKin. In this first tutorial, I will give a brief introduction and some tips of installation. So to use ChemPlasKin, you should have a Unix-like operating system such as Mac OS or Linux. Since ChemPlasKin has never been tested on Windows, I would suggest you to use Windows subsystem for Linux on a Windows machine. But of course, you can test installing ChemPlasKin on Windows by yourself. You should have some basic knowledge of Unix-like commands, Python conda basic knowledge, and Kantara experience. For advanced usage, you should have some C++ skills. Now let's move to the ChemPlasKin paper. You can use this ChemPlasKin paper as consider it as a high-level user guide. Especially when you have some theoretical questions, you can go back to this paper and check the governing equations. I have just created a Google group for ChemPlasKin. If you have any questions or thoughts, you can post under this group. And please help each other. And I may regularly check this group and help you if I have time. Now let's move to the source code of ChemPlasKin on GitHub. I'll briefly go through the installation steps. Before getting started, you should check your environment. As I said, ChemPlasKin has been tested on macOS and Linux, but not on Windows. But it can be for sure installed on Windows with WSL, standing for Windows System for Linux. Okay, if you haven't installed that, you just click the link. Yes. So here give you tips on how to install Linux on Windows with WSL. Okay. So with this installation, you will get a very clean Linux system, which may need to install many packages, even some basic ones. So if you are using WSL, click here, go to the node for WSL users. So you need better check GCC and G++ version to make sure you have C++ compiler on your machine. Well, even you are working on macOS or Linux, I would suggest you to first check this compiler. And for WSL users, if these two compilers are missing, install them install the build essential package, which includes GCC and G++. So just execute a sudo update and install the build essential package. Okay, good. Let's go back. Let's assume we are working on a Mac OS or Linux system now. First, you need to prepare the working directory. For example, here we prepare we first move to the desktop. We make a directory called ChemPlasKin projects. Then we get inside it. Now we need to clone the repository. Okay, conducting this tool, you should have two directory called Kantara and ChemPlasKin containing these two source code separately. Before installing ChemPlasKin, you should compile the Kantara original source code. Okay. So, oh, by the way, if you like Git is missing, you should install it, right? So let's check compiling Kantara from the source. Okay. So you should jump to the Kantara. Here are some quick starts suggestions. So, but before that, you need some compilation requirements to be met. Let's go to compilation requirements. Okay. So I highly recommend to use Conda. If you don't have Conda, first you check the Conda version. If it's missing, you can install from any of these, Anaconda, Miniconda, Miniforge. For example, I suggest to use Miniconda. Let's go to Miniconda. Okay, here. Okay. Here is a quick command installation. You can on different operating system. For example, on Linux, you just copy these lines to your terminal, and you should be able to install Miniconda. And after that, you can check. It should be here. You should check Conda version. It should be there. Okay. Okay. Let's assume you have installed Conda. So what is Conda, by the way? You can consider it as a package management tool, especially mainly for Python packages. So with Conda, you activate a certain environment containing all necessary Python packages. Let's go back to ChemPlasKin. So here I already provided a environment requirement file. It's here. Let's click in environment.yml. Okay, here you see this is compilation environment for Kantara library used by ChemPlasKin. So here we don't need Python package for Kantara. Since ChemPlasKin is written in pure C++, we don't need Python interface. So the name of the environment, we can call it CTCPK, and from the conda forge channel. And this dependency means all these packages should be installed to be able to compile Kantara. So we have Python scorn. So scorn is the building tool. We have remaining dependencies. So, okay, let's go back. Let's go back here. Okay, you can use this command to create an environment called CTCPK. Then you activate it. Okay, here on my machine, I have already installed Kantara library. So now we are under Kantara directory. So, okay, you can see the source code of Kantara. So after activating CTCPK, you should be able to see the CTCPK before your username. That means it's being activated. Okay, so you go inside this directory, which I'm already in. You check out the version and run scorns build. Okay, since I have already compiled my Kantara library, so it should be very fast. Typically, if you're building from source, from the scratch, it should take like 5 minutes up to 15 minutes, depends on your machine. Now I'm compiling, but since I already compiled, it will go through very quickly. Okay, you see, after the installation, you will see this compilation completed successfully. Okay, to run the test suits, scorn test, you don't need to run any of them, not even the install, because we don't need to install the Kantara Python library. Okay, you'll see this message upon successful compilation. Good. Now, let's obtain the external library for ChemPlasKin. You should create a new branch for Kantara checkout. Okay, that's what I recommend. We don't want to have some conflict with the original code, but it's not essential. Okay. Okay, checkout. We create a new branch called for ChemPlasKin. Okay. So I have done that. Let's check it. Git branch. You see, I'm under the branch of for ChemPlasKin. Before we were in 3.0. So now we fetch a source code of CPP bolos and mu parser. So CPP bolos is the electron Boltzmann equation solver developed upon the Python version of Python version called bolos. I call it CPP bolos because it's written in pure C++. You should go to the ext directory. So ext means external library file directory. Okay, so you go in there and clone the source code of CPP bolos. Now change the directory name to bolos for simplicity, and then you clone the source code of mu parser. So mu parser used for parse any complex mathematical expression for plasma reaction rates. Okay, so you put them under. Okay, you don't need. If you do this, it should be already there. Let's check it. Let's go to ext. Okay, list. You can see we have bolos. We have mu parser here. Let me show you the directory. more clear way. So you will have bolos, you will have parser, and some many other libraries. For example, Eigen, High Five, right, YML, and Sundice for the CVOD solver. Good. Now we need to update the scorn script under ext file. Okay, we go back to the Kantara root directory and just to override the scorn script under Kantara under ChemPlasKin project to the original Kantara um, directory. Okay, you will see it's been overwritten. Let's have a look at scorn script. Okay, it's here. Let's check it. So it was modified from the original scorn script. You will see here, this is the section that I inserted. Okay, add bolos and parser. So with these scripts, the compiler will be able to figure out two extra library, bolos and parser. It will be compiled together. Okay, after doing that, you need to extend the Kantara kinetic modules. So basically, you can do it manually if you don't use the CP command. It's just overriding original some original files. For example, the Boltzmann.h file will be added to the kinetics module. Okay. After doing that, you use the Kantara kinetics module can be extended to include the plasma reactions. Now we can stage and commit change. This is optional step. Now we compile a new library, okay, which I have done already. So the Kantara library is under the Kantara build lib. Let me show you. It's here. Kantara build lib. You'll see the dynamic library. Okay. This library would be linked to ChemPlasKin. For example, on macOS, you can see here ChemPlasKin private Kantara is being linked to the target. The target is ChemPlasKin. Okay, you don't need to do anything here. No action needed. This is just to explain to you how Kantara Kantara library being linked to ChemPlasKin. Okay, now let's build a ChemPlasKin. Before doing that, just make sure you have CMake and make. You can check it by CMake version. Okay, it's there. It has a version number, make version. Good. Okay, now you need to go to the ChemPlasKin. Okay, cd, go back to the ChemPlasKin directory. So here, because I have different version, so this is a release version that I'm posted on the GitHub. So now this is same as the same directory that I mentioned here. So you can list it. Okay, here's ChemPlasKin, which is here. Okay, release. Okay, this is the release version. So go back to the ChemPlasKin and make a build directory and go inside. Okay, that's because I already have it. Let's go inside. Okay, I have already built it. Let's remove all. Okay, okay, now it's empty. Okay, here's a recommendation. If it is recommended to clean the build directory if there are build errors, significant change of your project structure, or semi configuration. Okay, now I have just deleted the content of my build directory to clean it up. Now we do the same make dot dot. So these two dots means I refer the CMake list file one level above, because here you can see here is my CMake list file. Okay, my build file is here, so I need to use two dots to make the CMake know where the CMake list is. If you do this, okay, you will see you have error because you It cannot find CMake list. We do this. Oops. Dot dot. Good. So now we can compile the file. Compile ChemPlasKin. We do make. Good. Now list. Okay, say here. Okay. Let's check the directory. You'll see the executable ChemPlasKin is here. Good. Now let's test it. Go back. So again, if you are just modifying the source code or do some minor change, you don't need to clean it up. You just run make again. Okay. So let's run example. Use case to specify running case path. So here is the path to the control decline ChemPlasKin, ChemPlus property files. Okay. As I said, you should go one step back, one level of directory back, and use this dash log flag to control log level. You can put it here non-warning. So non means there's no log except the very essential arrow being printing on the terminal. Or you can use warning if you make some uh, if you run long a lot of passes. Warning give you the some essential warning message. Info give you like make assign something like a balance is the default setting, or you can use debug. If you code has some problem, just put log debug and tell you where the problem it is. Okay, let's run it. So this is example of H2O2 helicon mixture. Okay, this is the example in the paper test case 1, I think. Yes, this one. Okay, this with this example, you can fully recover the results in this section, which is in mouse paper ignition problem. Okay, so you can reproduce the results here. See, good. It's running very fast. Okay, just take 2 seconds. Yeah, on some machine I can make it like 1 second finish composites. Can be it's very fast solver. So you can see if you have a look of the output, it's runtime tell you uh where you are and the part number 9 is a nice number. So it's counted from 0. So 9 is 10th parts. So the DT and this is reduced electric field, gas temperature, electron temperature. So here is writing number density of this species. So CC there is a convention ratio, okay, of your fuse. We'll talk about later. Here's the power input of plasma, and yeah, your ignition delay time. It doesn't have much meaning right now because we are not igniting things. Okay, we're just running the fires, running the temp basics. So let's check results. Okay, um, we go inside the directory, cd sample. So good. See, its output is here. Okay, now we can run the plot. Oops. See, no module named matplot live. Okay, it's because this CTCPK environment, I think the current environment I'm using doesn't have this one. Okay, I would just on the deactivate. Okay, now I'm going to base environment. I think now I should be able to deploy it. Okay, you can see the production of O2 singlets. It's more fraction after 10 passes. Okay, so by the way, this CTCPK, this conda environment is only useful during the compilation. You don't need it when you are running ChemPlasKin. After compiling the source code, you can just leave it there. You don't need to activate every time when you run ChemPlasKin. Okay, good. So Yes, this is some tips of introduction. If you have some difficulties you cannot solve, post your question under the issue. You can go to the issue, uh, post some questions, or you can go to the Google group, leave a question or comment there. Okay. Now let's take a closer look at this test case of H2O2 HE. We have two input data files. Okay, um, specified in ChemPlus properties. And one is cross-section data, one is Mac file. Okay, so let's first take a look at it. This should be easier way. Samples, two. So basically, you have two files as input. The ChemPlus property specify the plasma and the gas physical properties. Okay, the control how do you run the simulation? Basically, for the time step, how when are you going to start it? Okay, and the output files and how you run the CVOD solver. So all the physical properties written in ChemPlus properties. Okay, here we have initial conditions, the temperature, pressure. Would you like to use constant pressure or constant volume? Would you like to use, okay, zoom it up. Okay, would you like to use hold the temperature as a constant? So here is a little bit tricky. Non-thermal, if you select non-thermal to yes, that means you hold the temperature to constant. Okay. If you hold it to no, no non-thermal means thermal. Okay, sorry, I made a little bit confusing here. No non-thermal means thermal, means you are evolving the temperature. Okay, be careful here. So plasma heat model. Um, we have two options, default and fleety. Okay, if you look at the paper, default is using the governing equation here. Okay, your heating source, plasma heating source, is calculated from individual electron impacted reactions. Okay, it's from here. So if you are using fleety, okay, your plasma heating source term coming from this one. Okay, this is a plasma heating source. It's more like a global model. But this default model is more detailed way. It's not modeling, it's a calculation. If you look at the input files, oops, okay, here is not very clear. So you maybe you can see it. So energy transfer, um, electrovolt. This is how much energy being deposited into the system. So this equation, this equation calculates all the reactions related to electron neutral collisions. Okay, so this is E. This is epsilon TH. TH is threshold energy. Okay, for each collisions. Okay, so this is more detailed model. But in if you are using the mechanism from coming from ChemPlasKin, there's no way. Usually they don't have this threshold energy to specify the how much energy depositing in each collision. But if you are using ChemPlasKin, for example, here air plasma, you will see here, for example, here's example of your rotational excitation. Here 0.02 electrovolt being deposited in this collision reaction, and here is all other this energy transfer entries represent the energy being deposited in the system. Okay, so this is a very detailed model. Um, okay, I would always suggest use the default, but you have to make sure you have this energy transfer entries. Okay, especially yeah for this electron impact reaction. If you don't have them, it means you don't. If you don't have this energy transfer entries and you are using fleety, what will happen? Okay, nothing will happen. Sorry, nothing will happen. But if you are using default but without energy transfer, your this means you don't have energy deposition into the system, right? Your temperature would probably even decreasing because there's no plasma energy. So heat loss model, no here because this is DBD case. Okay, so but as the paper said, the heat loss model should be triggered if you have high plasma deposition, especially for ping electrode. Okay, so this is C0 parameter. You can find this one in the paper. Is equation 13. Oh, by the way, sorry. So this is C0 is not exactly same as C0 here. Okay, so in equation 13, C0 divided by R squared is the C0 here. Okay, that's why you see it's not 1. Even C0 here, 1 is 1. Okay, it's 1 divided by R squared. You get this number. See, it's 1 divided by R number. So R this is the discharge radius. Okay, so you can tune this parameter to better simulate the heat loss from the diffusion, thermal diffusion. So this is the initial mixture composition in mole fractions. Okay, now we have H2O2He. The fuel name is specify the fuel name. This is where the conversion ratio you got. You remember here, you got conversion ratio, how much of fuel being converted. Electron density. So this is initial electron number density. You have to specify a number here. Okay. Otherwise, if it's 0, there will be never plasma inert species. But this initial number electron number density doesn't matter. You can put even you put 1E5, 1E6, it doesn't matter your final result because it eventually will reach like kind of quasi-steady state. If you look at this figure. You see, it doesn't matter which number you put at the very beginning, it will eventually become kind of quasi-steady. Okay, just put a decent number, 1e minus 1e4 or 6. Okay, and then is plasma parameters. Here you have to specify which species you would like to be specified by, configured by the Boltzmann solver. So we call it Boltzmann species. Okay, with H2O to He, of course, you have to include them because they are major species. And so this species represents, you want to include them to be figured out by the Boltzmann solver. The electron will have some impact with them. Okay, but here, of course, you need the water because also major species. But some other minor species, they are not essential because they are only consists of small fraction of your gas mixture, right? Imagine you have a gas mixture with many species, but electron probably collide with some like major species, right? So it depends on your cross-section data as well. I mean, on the fidelity you want to simulate. Of course, you make sure you have all the major species, okay? And make sure your cross-section data in LaTeX format contains all the species specified here, the Boltzmann species. Okay, you cannot put something, for example, if you put OH here and your LaTeX cross-section data doesn't have COH, you have some error because you cannot find it. Now this is great type for solving the electron energy distribution function EEDF. Okay, so the Boltzmann solver basically, sorry, it's 1D linear solver to get the EEDF. So you have a 1D grid. You have different option: linear, quadratic, and logarithmic. Okay, the quadratic should be sufficient. Okay, so we have grid size. Grid size is starting value. Of course, you should starting from 0 and end at 100 is this number. But if you have very high reduced electric field, you can increase number and points. How many points? The more points you put here, you slower the simulation to be, but you should get a more accurate result. But okay, mm, if you have some problem of CPV bolos, it's better to test it separately. You can compare it with Bosic and yeah, just run the CPV bolos solver and see where the problem is. This is E reduced electric field for NRP during the NRP high voltage bus. So here you can option to choose DC voltage to DC reduce electric field. And state DC means would you like to maintain the DC discharge after NRP discharges? Okay, here is no, means after 10 passes, year one will be zero. Okay, this is the frequency of NRP, pass energy, the input energy per pass. So this is very, very important parameter here. This parameter specifies when the E over N cut off. Okay, otherwise the electron number density would easily explode and your simulation crash. So because the growth of electron number density is exponential, look at here. Okay, so when it reach the each pass reach the deposit energy point one, it cut off immediately, so it doesn't shooting up. So the pass width, so this is not a very important parameter. You can put like 2 point, because as I said, the pass width is determined by the pass energy, not by the pass width. This pass width just gives some guidance. Okay, it's used for the first two passes. Okay, here are the criteria updating electron Boltzmann solver, T gas tolerance. So this tolerance means if the change between different time step, if the change of T gas or the reduced electric field exceeds this number, you should update the Boltzmann solver. Okay, so actually the T gas doesn't matter. Okay, even between 300 and 3000, gas temperature have very minimal effect on the EEDF solution. Okay, but I put it here. You can put it on a big number, maybe 5 or whatever. Okay. Um, but E tolerance, okay, you can put a small, even smaller number, 0.1, to make sure it update more frequently. So this is data file. Case, remember the case you use slash case. No, not slash, dash case here. That's it. Use this dash case, the case directory. Okay, so this directory would replace the case directory here. So used to access the cross-section data and mechanism file. Okay, always make sure these files are in valid paths so you can read them. Okay, and this is a control directory here. Okay, start time, end time, and how many passes you would like to run. So this simulation would end at maximum between end time and passes times pass period. Okay, so that's why you can put 0 here, because it will take 10 multiply by the pass period. Okay, so if you want to run longer time, for example, you would like to run 10 passes but make simulation continue for 1 millisecond, you can put a larger number here. So it will take n time instead of this n pass times pass period. So okay. Next we have time step parameters. We have DT1. DT1 is used for first two passes. Okay, because at the beginning it doesn't, the solver has no idea how the electron number density involves. It uses a fixed smaller delta t to evaluate the electron number density evolution. Okay, this is maximum time step you allowed. Okay, you can adjust this. So now it's adaptive time step for the main time loop. Okay, So ChemPlasKin uses adaptive time step, except for the first two passes. So this is pass extension, which represents the fast relaxation of pass influence stage. Okay, so because after you're cutting off the pass, there are still some fast reaction going on. So you probably would like to use small delta t as well. So this is n step in pass means number of time step in pass discharge. Okay, so let me show you something. So this figure represents the dynamic time step used by ChemPlasKin. You see, each black dot represents the time step. You see, during the pass, because the electron number density increases exponentially, so we also logarithmically reduce the time step, then relax it to a bigger value. Then we use fixed one. So we dt1, dt2, and dt3. So we assume a growth or decay order of k during the period. 0 to Tn. Tn is the peak of the electron number density. So when the plasma energy reaches the designated number, for example, 0.1 millijoule per centimeter cubic, it will cut off the electric field. Okay, so as I said, for the first two passes, it uses a fixed delta t to have a memory of the decay or growth order. Then it can determine okay, how should I adjust the delta t? So if you are adjusting these numbers, put a bigger number instead of 400, you put like 600 or 800, and here you also increase number. You have a smaller delta t. Okay, so these two parameters are used to adjust delta t. So dt max here is 10. You can put the 5 maybe. Is maximum temperature increase per time step allowed. Okay, although we have a lot of uh, you use dynamic time step, we want to capture the steep gradient of ignition during the ignition process. We need to control that as well. This is dt below t eq. So what does it mean? So we force simulation ends when t reaches equilibrium temperature minus this small number. Okay, so you will see. I will explain to you later in the code when we read the code. So we have equilibrium temperature. Okay, during after the ignition. So for example, hydrogen, oxygen, like for example, 2,500 Kelvin. Okay, so if you put 5 here, which means when the temperature reach 2,500 minus 5, which is 2,495 Kelvin, the simulation cut off. Here is CVOD solver tolerance. Okay, the relative tolerance, absolute tolerance. These are important parameters to adjust the CVOD precision. We have output log, okay, and the right species. Okay, if you uncommon this, you comment this one, you write all species. Okay, sometimes if you are species too much, over 100, for example, and you only care about few of them, you don't want to write all. You can comment this one and write species. Put what species you would like to write in your output file. Okay, good. So what do we have? We have data input here. We cover this. So the data directly contains how to pronounce it, LexCat. It's cross-section data in LexCat format for CP bolos. Okay, if you go to this website, you'll see a lot of cross-section data. Okay, I'm not an expert of this. I don't. There are many database. I bet there's some database are better than other. Okay. So you have plasma assisted combustion kinetics. Yeah, maybe I should change the name because it's not just for plasma assisted combustion. So you have unified gas plasma mechanism in YML format. Okay, just that have a plasma mechanism developed by Chen. It's a very good paper, and this is one of the best mechanism has been validated across a broad range of test cases. Good. So you see this fire in encompass everything. It's not like ChemPlasKin, which has thermal transport reaction. So this YML file contains everything, including thermal properties and transport properties, right? So let's move to the reaction part. So first, okay, if you are familiar with Kantara, you should be able to see this before. So this is the original GI methane air combustion mechanism with 53 species. Okay, so here it's nothing special. So now let's move. Oops. Okay, now we have air plasma mechanism. I also post some of these examples on the in the paper. You can read it out. Okay, this is any transfer entries. Okay, an optional parser tool called PLASKIN.py is available to convert ZD input mechanism file into YML format automatically. Okay, ZD kinetics parser tools. Okay, here I have a brief introduction of these parser tools here. So just make sure you have installed all the packages for your Python. Okay. Um, when you run it, you probably give you some error that one of these packages are missing. Just install them one by one. You should be fine. Okay, this is useful tool. But remember, as I said, for ZD input, there's no energy entry, right? You don't know how many energy being deposited in the reaction. For example, this one is excitation. Uh, So you probably, I would suggest you manually add the plasma transfer entry. Okay. Um, so what is this value? How to edit this value? Okay. For example, this is let's take this example. So electron collide with nitrogen. Okay, nitrogen become excited, vibration excited. But since we aggregate all vibration states into only one E vibe N2, so we don't have N2 vibe one. You see here, you see this is the simplification of species. We don't need to include all the species V1, V2, V3, V4, V5. Okay, this can significantly reduce the total number of species to be calculated. So here's the process. It's N2 to N2 V1. Okay, so if you look, so where is this number coming from? Where is this 0.291 electron volt coming from? This is threshold energy to excite N2 to the V1 state. Okay, if you look at the latex data, let's see this one. Okay, you see, this N2 is the effective one. Don't worry. Okay, look at this excitation. Okay, this is excitation. This is rotational. This is excitation. So N2 to N2 vibration 1, you call this 0.3 EV. Okay, you see it's slightly different. Slightly different. So this I'm using this value from Chen's paper here at I mentioned beginning here. Okay. Yeah, this paper. So it could be slightly different from the cross-sec data, but it's not too much. When you are developing your own mechanism and you put the energy transfer entry here, so this is the threshold energy is how much electron energy being deposited into the, you can think it as energy lost during this process, okay? So this is energy entry of electron you should put in. Okay, let's go back. Okay, I think I have covered the introduction part. So again, if you have any questions, I recommend you post it in under the issue or the Google group. Thank you very much.